Hello, good evening everyone. So I am Shubhanu Haldar from I am PhD student at IIT Delhi. So today we will be starting our session for the week 7 of this operating system. So like the last few classes, we will be solving some questions today also. So today we will be starting our session for starting our topic on process synchronization. So, so there are there. So we have some question with us. So first, we'll be try to understand the inter-process communication and the synchronization thing. So what are the race conditions? What is a race condition? Okay, and what is a critical section? Like this kind of question. We'll be trying to answer first. So then we'll be moving towards our regular question answer session. Yeah. So fasting is that the what is it for? Okay, so what is a there are few things which needs to be answered, like what is a race condition? Okay, so the final output of suppose you have a process. Okay, so let me process example. So in process P1, so you will start like process P1 is like this. You have some comments, and you have a statement like count minus minus. Then also you have some statement. Then here it ends. In process P2, there is also statement is same. Okay, but in the last line here you have count minus minus. Okay, then your program ends. Okay, so and here in between your count value is 5. So 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 your count value is 5. Okay, so now this is important that and this count value is shared by this process and this process also, process P1 and process P2 also. Okay, so maybe there are some information of the of the count, like okay, so uh, how can I can write like this, like move count to R0, then increment increment R0. Okay, then move R0 to count. So these are the steps for doing count plus plus. Okay, so for count minus minus, so move count to R1. So R1 is a register basically. Okay, R1, R0 is a register. So what you will do that, so you will be first, so this is a variable. So you can't do calculation in this variable. So what you have to do that you have to move the variable value into a register. Then you can calculate something. So you are moving the count variable to R0 for doing some calculation. Then you are incrementing R0. Then again moving the register value to the count of the variable value. Okay. Then in the second you are here decreasing R1 and moving R1 to count. Okay. So what are the so in this scenario, what can happen that P1 can run first, Okay, then P2 can run its statement 1, 2, 3. Are you seeing that? So you have to do count plus plus or count minus minus. Okay, so what will happen that, so line for this count plus plus, the, so this is plus plus. For this count plus plus, are you getting, like in P1 there is count plus plus and P2 there is count minus minus. Okay, so both are, so what are we trying to do? So we have a count variable which is shared by both of the process P1 and process P2. Okay, now, so these are the steps of the count plus plus. Okay, so this is a low level language. Okay, this count minus minus is the step for low level language. Okay, so and you know that computer is very fast to doing its operation. So first we are assuming that first process P1 runs, then uh, this step number 1, 2, 3 all have done like this, 1, 2, 3. Then we came to this one. We came to this P1, P2, P3. For P2 statement 1, 2, 3. Okay. So then what will be the count value? Okay. So count value will be 5 because you will be incrementing 6. Okay. For this one, you will be incrementing 6, and then whenever you have already incremented, then you'll decrement it to 1. So 5. Okay. Now what happened next? So suppose P1, for P1, it is like P1, and for P1 line number 1 and line number 2 is complete. Okay, what line number 1 says? That line number 1 says that make a register R0. Okay, then move the count variable 5. Okay, and increment R0, that is 6. Okay, so the count variable will change when you will run this line. Move R0 to count. That 6 is incremented in the register, but there is another space in your CPU. So that is not updated yet. Are you getting my point? So what happens that after this, in P2, for P2, okay, 1, 2, 3 happens. So 1, 1, 2, 3 means that what P2 does, P2 decrement it. So P2, what P2 will do, P2 will take a register R1. So P2, so this is the program of P2 for so this is the line for P2. This is the count minus minus, because you see P2 is doing count minus minus. Okay. So what P2 will do, P2 will keep the variable. What you see here, that R0, at R0 you have already implemented this line 1 and 2. What is moving and incrementing? It is done where the increment has been done. So it has done in the R0 register, no, not in the variable count. So variable count still have 5. Are you getting my point? Variable count still have 5 because you have done all the thing in your register only. Okay, you have not implemented this time. Okay, in between, this process P2 has decremented it. So process P2, what does it do? It will decrement it to 4. Okay, because it will decrement it, and it will also move. It will also move it to count. Fine. Now, in this scenario, you have run your last step. P1 is equal to 3. So what it will do? You know that uh, P1 P1 for P1 line number 3, what it will do? It will move back the value 6 to the count variable. So it has 4, but it will be 6. So here your count variable value will be 6, the final count variable value. So are you seeing that because of this execution, that you have only written in C program that, okay, do count plus plus, do count minus minus. So count variable will be 5 plus 5 minus. So that is 5. But see, there are in between so many steps for this count plus plus, as I have shown here. Okay. Because of this, the C value will be will will not be, you can't expect the C value as you have written your program. Okay. So this is the scenario. So I can give you another scenario. So the question is, I am giving you the situation. P1 first, uh, run these two line 1 and 2. Then P2 run these two line 1 and 2. Then P1 run this line, and then P2 run 3, run this line. Okay. So this is P11. This is P11. This is P12. This is P13. P21, P22, P23. Are you getting my point? So if there is any confusion, please write in the chat box, or you can unmute yourself and ask me. So please tell me what will be the value of C here at the end of this program. Please write in the chat box your answer. So this is the question. Is it a hard question? Okay. Mhm. So what are we trying to do? That okay. So we are trying to do. We know that for P1 and for this one P12, what it will do? It will execute these two lines. That you will be creating a variable R0. In your C, it is 5. Okay. You will be creating a register R0. You will be moving count value to R0. Count value to R0. I don't know. Okay. So what it will do, that R0 value will be 5. Give me a second. My pencil is not working. Yes, Diksha, you are right. Absolutely right. It will be 4. Give me a second. I don't know how to do. Okay, sorry for the delay. So R0 value will be 5. Okay, because of this one. That count R0. Okay. Then what he will do, that okay, this is done. Then this two, this 1 and 2 is done. Then for this P2 will be 1 and 2. So P2 will run. P2 will make a variable register R1. then it will move R1 the value 5, then it will implement it to 6 and it will decrement it to 4. Okay, then what will do, P1 will move R0 to count. So this is your C value. Okay, so P1 will move it, so C is equal to 6 now. Then P2 will move it, then so it will be 4. Okay, so C value will be 4. Got it? So this is the situation that the final output of your program is depend on the order on which the process are getting executed. So actual value should be 5 because plus 1 and minus 1. Other happens due to this inconsistency of this program. Okay, so this should be so because this happens because the both process using the critical section. Shit, what happened here? So so this happens because this count section is this count will be called as a critical section. Okay, so count is the critical section. These terminologies are important. So there is a part of code which the both process is trying to share. The common section or critical section in both P1 and P2 is the count part. Okay. Uh, Now, so you know about the critical section. So critical section is the part of the program where shared resources are accessed by the process. Now there are something called okay called what are the requirements for synchronization mechanism? So requirements are there are primary requirements. Okay, primary requirements are mutual exclusion and progress. Okay, I'll tell each of the topic uh, about this. And secondary requirements are your bounded waiting, but it's bounded, and architecture neutrality, or you can say as portability. So what does it mean basically? So the primary requirement and secondary requirement. So primary requirement is that mutual exclusion means no two processes should not definitely provide no two process should not enter in the critical section. Okay, that mutual exclusion means so you have the count variable. So at the same time, both processes cannot uh, enter into a critical section. So one process like P1 or P2 have to do first. Okay, right? Then like you have one mouth only, and you have some pasta and some chow, like roti and chow. So uh, ideally you can't eat like you have to eat chow first or roti first. Okay, so this is the scenario. So your solution should definitely provide mutual exclusion. So any synchronization mechanism you came up with that must provide the mutual exclusion. Okay. Otherwise, there will be race condition. So this is the thing that there will be a thing named race condition. Like in race condition, both processes will be trying to use the same resources. Another thing is the progress. Okay, progress means if one person doesn't use suppose you have went to a mall. Okay, so if one person uh, don't use the trial room of the mall, so he will not stop other person for going into the trial room. Okay, so there are limited number of trial room in the shopping malls, so no one can force any other to go to the trial room. Okay, so this is the thing. Another thing is bounded waiting. Bounded waiting means if you are going to the trial room, you have to tell the time when you will be coming out. So that scene should not happen that only one person is always using the trial room and other is waiting forever. Okay, so these are the things. Another thing is architectural neutrality or portability. So this is this is uh, very intuitive that uh, you are using your code, you are writing your code a portable one so that you can use it in all kind of architecture. So so primary condition must satisfy for synchronization mechanism. So the synchronization mechanism are busy waiting and no busy waiting. Okay. So busy waiting is if a person enters the trial room, other person will continuously knock the door. So this is called the busy waiting. So no busy waiting is if a person enters the trial room, the person will go and sleep until the person come out. Okay. So are you getting the point? So if someone is using the trial room, so busy waiting this, he will be knocking the door so that he can understand that someone is waiting always. And no busy waiting is if a person enters the trial room, the other person will go and sleep. Okay, fine. So how we will implement this type of concept? So we go to the shopping mall, we face this kind of situation, but how should we implement this concept in our computer science? So this is the thing. So there is a term called log variable comes into the picture. Okay. So what it will do? Give me a second. Yes. So log variable is a log variable is a software mechanism implemented in user mode. So this is a software mechanism. So user mode means, so you know that this is not a hardware system implemented in user mode. User mode means this is not a part of operating system. So this is part of like some user will write the code and some user has implemented this kind of system. Okay, then okay. So what I do like, so what the code will look like while log not is equal to 0, log is equal to 1. Then you have critical section, then you have log is equal to 0. So this is called the entry section. This is called the exit section. Okay. So this is the scenario. Okay. So here log is equal to 0 mean it is bracket. Okay. And log is equal to 1 means it is occupied. Got it? So if someone goes into the trial room, then if someone wants to go to the trial room, okay, so the solution was you have to keep the door knocking. So how we will do that? How we will implement that? using this while variable. While lock not is equal to 0. So you'll be waiting. Okay. So if the if you have entered the critical section, so if you have seen that log is 0, then you will enter the trial room and uh, uh, close the trial loop. Okay, that means that lock is equal to 1. Okay, then you will use the critical section, like you will do your work. Then whenever you come out, then you open the lock. So that is lock is equal to 0. Okay, this is so simple. So what does it provide? So any solution, any mechanism, any synchronization mechanism will be looking. So we have to look for these four requirements, that if we have to see that if this algorithm or this solution is providing this four requirement or not, that is mutual exclusion, progress, bounded waiting, architecture neutrality. Okay, so the question will come like this. So you will be given this piece of code. So then they will ask you about that which which requirement is not satisfied in this program. Can anyone tell me that which requirement is not satisfied in this program? So we have mutual exclusion, we have progress, okay, we have bounded waiting and portability. So so mutual exclusion says that no two processes should not enter the critical section. Okay, so but here you can see that more than one process can go to the critical section in a particular time. Okay, so because if you see the implementation of the log variable like this, like this moving, implementing, and like this, so this solution doesn't provide the mutual exclusion. So suppose someone is in the trial room, this implementation does not also provide the progress, because there is no motivation here, like no part of code is given here, so that a progress is assured. Okay, otherwise these two are fine. So like this log doesn't provide the basic requirement. So these are the primary requirement, these two. Okay, so this solution doesn't give provide the basic requirement, that is mutual exclusion. Is that if we use this process, two or more process can enter the critical section. So this method is a invalid method for the process synchronization. So what do we do for the to overcome this situation? So we implemented such thing called test set lock, okay, or TSL. So which follows a round robin scheduling kind of algorithm. So where basically this happens: load lock R0, store 1 into the lock. So this is a atomic process. Okay, so this will happen in a single. So then second instruction will be compare R0 with 0, because we have seen that while for this one, while lock not is equal to 0. Okay, then your third instruction will be JNZ step 1. Okay. Jump. JNZ means jump. Okay, so this is the thing. So for TSL, mutual exclusion and progress is guaranteed. Okay, but but it is the architecture dependent. Okay, you see that you have implemented something that this should be atomic. So this your program is architecture dependent. Okay, so you have remembered this four requirements. So this is a in this solution that mutual exclusion is guaranteed, progress is guaranteed, but this is architecture, this portability, architecture dependent is not there. Okay, so and this condition may bounded waiting may also validate here. So so there is one more problem called priority inversion, which is so suppose so suppose two processes are suppose P1 and P2. There are two processes who want to use the critical section. So there, this is the entry point, this is the exit point of the critical section. Then here P2 is with higher priority. Okay, if P2 is with higher priority, but as P1 has reached earlier, I have told you that this follows round robin scheduling algorithm. So in the last class we have seen round robin scheduling algorithm. So here you have seen that P1 has arrived and it has some value as 0. Okay, okay. So P1 has arrived earlier and it has value as 0. Okay, so then, but P2 has the higher priority. Okay, but to finish the task, P1 also need the CPU. That's why there might be a spin lock kind of situation that like P1 is arrived earlier. It is in the it is using the trial room, but P2 is the VIP one. Okay, so P2 is the VIP person, so he needs to use the CPU also. Okay, so this how the this priority inversion problem comes. So there are also some kind of solution to this. Okay, so so another thing is okay. We see some question. Okay, now okay now okay. So we will see some. We'll see another example again. Then we'll go to the thing that how we handle these situations. So there is something called disabling interrupts. So this is a hardware solution. So when a process is running, send an interrupt, and for the interrupt, the operating system kernel will take the control of the CPU. So if the process is running, so you will interrupt it from the. So this is a hardware kind of implementation. So operating system will take care of that. Okay. So so this disable interrupt will provide you the mutual exclusion and progress guarantee. Okay. So another thing is that that is called uh, uh, yeah, one thing is called Peterson method. That is called so here the thing is that for this kind of approach for this process, so where there is we want to implement the strict alteration approach or turn variable, so that each of the process can use the CPU. So we use a variable called interested variable. Okay, so if someone in interest, so that they will keep the variable as 0 and then they will switch. So this kind of thing is there. Okay, okay. So these are the things. So we'll see some question here, then we'll be moving towards another points. So yes, so this is the question that which of the following is a synchronization mechanism used to solve the critical section problem? Yes, semaphore is the synchronization mechanism. Okay, next. Yes. So what turn variable does basically? So you have one variable called mm you have two processes P0 and P1. Okay. So what we'll do that so this is the non-critical section and this is the CS, this is the critical section. So this is the non-CS. So interested 0 is equal to 2. Okay. That means this process is interested. Okay. Also, there is a array 0. So this is a array kind of implementation. Okay. So while interested 1 is equal to true, then you can enter the critical section. Whenever you will go go outside the critical section, will do as false. Okay, got it? Can anyone tell me what should be the condition in this critical while you can write your answer in the chat box. Please, if you can, please write the answer in the chat box that what will be there in, in this solution. Yes, 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 exactly. While interested 0 equal to true, then it will enter the critical section. And whenever this is done, they will say that okay, add 1. Okay, I have done. I am not interested anymore. Okay, got this? Okay. Now this is your next question. Oh, okay. Tell me one thing in this question that this is fine that we have understood the mechanism here. Okay, tell me one thing that what about the mutual exclusion and all progress? Will this happen? That mutual exclusion and progress, will it happen? So these both two will happen. Okay. So mutual exclusion is guaranteed because they are going to critical section in two different conditions. So the conditions are different here. Okay. So this is why they are going into the critical section, and so both mutual exclusion and progress is guaranteed. Okay. Now, so if both P0 and P1 uh, process only first time of the entry and get preempted, then both will be in a while loop. So that will be a deadlock situation. In the next chapter will be after we are in the chapter of process synchronization. So in the next chapter we'll be looking at the deadlock condition. So this is an example of the deadlock condition that you have seen in some classes ago. You have seen what are the process state, like ready to run, from run to bounded, run to wait to ready. So there are some process transition diagram were there. Okay, so you know that there are something called preemption and non-preemption. Like if a process is running, then it can like stack in the middle of the process. Okay, so it has run some part of its code, then it can got stuck, then it will run the other part of the code. Okay, so this is the scenario. So here, so for this scenario, your interested variable, like you have run the interested variable and while variable. Okay, so and also you have run this one and this one. Okay, so and your process got, so after this one your process got preempted. For this one also your process got preempted. So you have lost all the things. So you have not accessed the critical section yet. So what happened then? This will be a deadlock because everyone is saying that I am interested and I am interested, but no one is making it false. Are you getting my point? So this thing will be a deadlock. Okay. So now try to solve this question. Okay. So this A is the right option. That's fine. Okay, we'll come to the next question. That this one. This is a. This is okay. So for the test set instruction, I have already told here, so I am not repeating it. So I have done the test set instruction here. Now the so okay. So this is the question. So if you can write the options in your notebook. Then you can try. So there are five options: A, B, C, D, E. Okay. I don't know how to share this. Okay. So I think this will be. I can see the all options here. Yes. The right answer is A. Sir, 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 थोड़ा सा नीचे. I'm recording something. So yeah. So this is the right answer. So we have seen this already, right? So we have seen the what is the Peterson. We have seen what is the Peterson algorithm for solving critical section problem. So we have just discussed about this. Yeah. Okay. So here I want to give you a question. Okay. Let us move on. Come later. Yes, C is the right answer. So only Diksha has given the answer, so I was waiting for another response. C is the right answer. So I have already seen, I have already told you about all the things. Yeah. So one question I'll write here. So that is, so this is a question from like GATE examination. The question is the following program consists of three component software and three binary single code. The single codes are initialized as S0 is equal to 1, S2 is equal to 0. So process P0, process P1, process P2. While true, weight is 0, print 0, release S1, release S2, wait S1, release S0, wait S2, release S0. Okay. So question is, here the question is, how many times will P0 print 0? Okay. So this is the question. Okay. So another some to say that yeah. So in the entry section, and this is the exit section. Yeah, entry section P B or P. If there is P, there we will be getting in the question that P is also given. Okay. Or you can see down, up, or you can see wait, then signal or release. Okay. So we have used wait and release here. So we have not used down or P. Okay. Are you getting the point? That for the entry section, you will be you can see the P or down or wait, and the exit section you can see the P up or signal. Right? These are the scenarios. Okay. Now tell me that how many times. So this is the question. How many times P0 will print 0? So try to solve the question. Then tell me. It will take some time. So I'll be back after some time. So before solving the question, so before solving the question, so we'll be doing some concepts about binary semaphore and counting semaphore. So what are the semaphores? So semaphores are basically a variable on which read, modify, or update happens. Okay. Uh, Atomically in kernel mode or no function. Okay. So the idea is clear from here. I'll come to the answer, Ishan, like how many times. So first thing is two types. One is counting. Counting means it takes value from minus infinity to infinity, and one is binary. Binary means it will take value from 0 or 1. So it is also called as mutex. Mutex or binary semaphore. Okay. So semaphore is an integer variable which is used in mutually exclusive manner. Okay. By various concurrent or cooperative processes in order to achieve the synchronization. Okay. So how counting semaphore is implemented? So first talk about counting semaphore. What is a counting semaphore? That so here you will be extract semaphore. You know this is a user defined variable. Whenever you extract this thing, so this is a user defined variable. Okay, like you write int now, so then you can use semaphore like this as a variable. Okay, value, and you have a q because you are counting. You have so many values minus infinity to plus infinity. So you are using a q type value. And what will be here? So you have one instruction called down, semaphore is, and you have one function called up, semaphore is. Okay. So here s dot value is equal to s dot value minus one. If s dot value less than zero, then it will you will put process in your process control block in L and then sleep. Okay, else will do return. What is the up statement? Up statement is if s dot value is equal to s dot value plus 1. Okay, if s dot value less than equal to. Here there is no equal to. Here there is a equal to 0. Then select a process from L. L means this queue, and then wake up. Okay, so counting semaphore can take positive and negative both values. Okay, so if value is negative, that means uh, how so if there is -2, that means there is two process, that is number of process are waiting to enter the critical section. Zero means zero indicate that no more processes can enter into the critical section. Okay, so in a critical section, more than one process can enter at a time. Okay, you know this one. So that number is decided by the operating system. So how many process can enter into the critical section, that will be decided by the operating system. So any positive number means that much of process can take place in the critical section in this moment of time. Okay, so my question is, a counting semaphore was initialized to 10, then there is 6p. P means wait. P or wait, anything you say. And 4v. V for signal. Okay. Operations were computed on this semaphore. Then what is the result now? Can anyone answer? Yes, it is 8. Like 10 minus 6 plus 4. Yeah, that is 8. Yeah. So, now this comes the binary semaphore. Okay. So what is a binary semaphore? So there is thing called binary semaphore. We have shown the counting semaphore. Now binary semaphore is, we have a structure the semaphore. We have kind of enumerated value 0 1. Now we have to type L, then we have, so now you have to implement the down B semaphore S S dot value equal to 1, then S dot value equal to 0. Else put the process or process control block in S dot L. Okay, then now now okay. So this L this L contains this L contains all PCB corresponding to process and got blocked while performing down operation unsuccessfully. So this enum indicates that the variable value can only have two options, the 0 and 1. Okay. Now here the s dot value is equal to 1. So this means that this indicates that the critical section is still available. Okay, critical section available. Okay, and you can perform the down operation successfully. Okay, now if the critical section for in this case, if the critical section is not available, the process will be added to the queue L. Okay, so this is your queue. Okay, if the critical section is not available, so you will be added to the queue, and it will go for sleeping. Okay, when critical section will be free, this process you are waiting, that will be okay now. So you'll be okay now. Okay, so now in the up section, so if up never stop any process from going to go up never stop any process from going into the critical section. Okay, so this s dot so here we check just only that s dot l is empty or not. That means no one is blocked and no one is in critical section also. This statement means no one is blocked and no one is in the critical section. Okay, now come to our question, that this one. Yeah, so here what will happen, that so as so s0, we have two variable, s0 and s1. Okay, s0, s1, s2, three variable, s0, s1, s2. Okay, so as s0 and s2 is fixed, initialized, so s0 is fixed, s2 is fixed. Okay, so now write like this, s0 is equal to 1 and s2 is equal to 0, and s1 we don't know. Okay, now what is happening? So how many time p0 print? 0. So s1 can have two values. So now as these two are fixed, what will be value of s1? It will have it can have two values, like, which is 0 or 1. Fine, fine. Now what are the options which can happen? So that thing we need to discover. So if we write like p0, 1, 2, 3, so we're seeing this like, so this is like 1 down, 2, 3 up, 4 up. Okay, 1 down, 2 up, 1 down, 2 up. Okay, So so you have three processes. So you have the shared variable s0, s1, s2. Okay. Now, so there will be many more possible cases of running uh, this one p0 to p2. Okay. So for this case, here have you run all the information p0 1 2 3 4 p1 1 2 p0 1 2 3 4. If this is the process and also p1 1 2 3 4 and p0 1, then the out will be 3 times 0 0 0. For this p0 1 0, p1 and 2 will be drop will be released. P0 this for this 0 will be done. P1 2 yes 3 times. So it will be 3 times. Okay. In the base case 0 will be printed 3 times, and in the worst case scenario, if p0 1 2 3 4 p2 1 2 p0 1 2 3 4 p2 1 2 and then p0 1 2 3 4. In this scenario the output will be 0 comma 0. So 3 times or 2 times, so this will be the answer. Okay, now try to solve this question. Yes, both of them, safety and newspaper. Sorry, sorry, sorry. With this question has also two options. Like, Okay, so here the answer will be the this one. For this case, we will not have a deadlock. Okay, for all other cases, we will have a deadlock. Oh, sorry. Okay, so I'm saying that for this, so E will be the right option. So for this case, there will be a deadlock. Okay. So how will you decide about the deadlock? So can anyone tell me that how you are deciding about the deadlock? So here Pi to Pj shares a semaphore variable t initialized at 0. So semaphore variable t is 0. Okay. So do you know this is a there is nothing is written here. So is it a binary semaphore or a counting semaphore? So we assume that it is a binary semaphore. Okay. So it has on takes on it can takes only two values, zeros and one. Fine. Now you have to process this thing. Okay. So this for this one process pi to pj, you have so many processes you have, and this is process pj. So process pj says that signal t, then so you have to basically find the situation where that I have seen the signals mean, so wait and see, entry and exit. Entry is wait, exit is signal. Right. Entry is wait and exit is signal. Yeah. Okay. So you have to find a situation where, So suppose suppose, so which leads to a deadlock free. So for suppose your signal is you're running process pi first, so signal is 0. Then you are again running exit. So exit will say exit. So here what does it do, that it will just change the value. So it will become 1. Now you are running statement 1. Okay, you are running statement 1 is fine. Then you got preempted here. Okay, at this point. Now you are running process P1 and wait 1. So wait T, what it will do? So here suppose this is 0. Okay, so you can run this statement here. Okay, so wait, this wait will make it 0, because wait means down and signal means up. Okay, signal mean up, wait mean down. Got it? Now here whenever you have reached here, so you will be doing one wait operation. Wait means down. Okay, but you will not be able to down it anymore because it is already 0. So there will be a deadlock situation. Okay, so in this situation, whenever signal are in there is in correct way, signal T and wait T. So this in this situation there will not be any deadlock situation. But here in this situation you see all are wait. You have a variable T which is 0. You are saying that okay, you down this. So this will not happen. Down this also will not happen because nowhere it will become 1. And for statement 2 also, like for this option also, wait and wait, it will never down. Yeah. Okay. So okay. So this is the next lesson. Yeah, so the answer is all of the above. Yes, C is the right answer. Uh, so yes, semaphore and monitor. Okay. Next question is Yes, operating system in of the operating system, a resource allocator monitor is a synchronization construct for managing shared resources. Okay, so and why this is used? Yes, mm, this is right. So resource allocator monitor is used for allocation of resources among multiple processes for the deallocation of resources from multiple processes to provide a high level abstraction for shared resource use to ensure mutual exclusion among competing processes. Yes, here the processes will be resumed in a priority based order. So this is the answer. So which of the following statement is true for resuming process within a monitor? So monitor process will be resumed in a priority based order. So it is a priority. The problem will be that given priority. Yeah. So how this happen? So initial value of t is equal to 10. Okay, t is 10. So the weight operation will so p1 performs weight. So then it will be decreased by 1. It will be 9, right? Then p2 perform signal. Okay, so it will be 10 again. Okay, then p1 p3 performs weight, so it will be 9, and p4 performs weight, so it will be 8. Wait. Yeah, Diksha, it is right that. So this is 0. Yeah, right. This is the correct answer. B is equal to 1. Okay. 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 Thank you everyone for joining the session. So I think this was all from my side for this week. Okay. So we will again meet in the next week then. Fine. Oh, sharing the notes. Okay. Yes, I've shared. Uh, you can get that from the shareable folder. Okay. Yeah, thanks a lot. Thank you everyone for joining. So we'll meet in the next week.